Hi everybody and welcome to our AQA GCSE Physics Paper 2 exam walkthrough, and today we're going to go through each of the main units, what you need to know for each unit, and give you the opportunity to practice some exam style questions and some revision clocks as well. So let's get started. So paper 2 is structured in the exact same way as paper 1, which will be for triple science students an hour 45 minutes and worth 100 marks, making up 50% of your GCSE, whereas for combined students you'll be doing a 1 hour 15-minute paper worth 70 marks and comprising 16.7% of your combined science or double science award GCSE. And each of these will be a mix of multiple choice, short answer, some structured like responses such as tables or diagrams, or open response as well. So the topics covered are P5 forces, P6 waves, P7 magnetism and electromagnetism, and then for physics students, P8 space physics. And for the required practicals for these are forces and extension, acceleration, waves, light, and radiation and absorption. And light is a triple science practical only. But there's a few different things they might ask for each of these practicals, so I appreciate this is quite small, but let's go through each of these in turn. So forces and extension, they could ask you to describe how to investigate the extension of a spring, identify the control variables and suggest improvements to increase accuracy. They could ask you to plot a force extension graph given some results that you've been provided with, and potentially identify either linear or non-linear regions. And they could also ask you to calculate the spring constant using the equation, which you'll have on your physics equation sheet, using some results that you've been given. For acceleration, they might ask you to describe the method for investigating how mass or force, because we looked at both on the required practical, affects acceleration using, could be trolleys, ramps or light gates. So that it could be a situation that you recognise from the practical. It might be slightly different, but the same principles will apply. They could also ask you to use a velocity time graph to calculate acceleration, or explain why a ticker timer or a light gate improves the accuracy of a measurement. And finally, as with all of these, they could ask you to identify the independent, dependent or control variables of that practical. For waves, they could be asking you to describe that method, so describing how to measure the wavelength and frequency of waves in water, and also to calculate wave speed using our equation. They could also ask you to state how to improve accuracy or reduce errors, or interpret diagrams of wave traces from a different set of results. So for triple science students, for light, you might be asked to draw or label a ray diagram showing the light entering the glass box, or on the other side reflecting off surfaces. And they could ask you to measure the angle, or calculate rather, the angle of incidence or refraction, and potentially explain the results you've seen using the principles of refraction. They again ask you to identify the dependent or control variables, and also to potentially suggest how to reduce uncertainty in that measurement. And again, that's something that they could ask for all of these practicals as well. And then finally, for that radiation and absorption practical, you could need to describe a method for comparing those surfaces absorbing radiation using that block, identifying the variables and suggesting improvements for controlling heat loss, which is kind of linked to our P1 topic as well. You also might need to explain findings using your knowledge of infrared radiation, and evaluate limitations in experiment design, which again is relevant to all practicals, but is often asked for this radiation and absorption practical. And with all of the practicals that we've described across all of the sciences, you need to make sure that you know your hypotheses, your variables, the equipment method, data collection method, the data visualization method, and some evaluative points as well. And if you've got all of these, it could set you on your way to being able to be confident asking all of these types of questions that they might ask. So in this video, we're going to do things differently to how we've done them for the other ones. Rather than going through some example questions here, I'm going to focus more on the content of the units, and then give you some exam questions to try yourself, or the revision clocks to go through, just because these topics are fairly big and it doesn't feel like going through just a couple of different examples will give you a fair representation of what you might expect to see in your exam. So instead, we're just going to go through each of the kind of content areas in turn. So let's start with forces, and I just wanted to kind of discuss first why P5 questions and all of the units in general can feel quite tough for physics. So the force questions often combine maths, diagrams and tricky languages we're not used to using in everyday language, which can make them very intimidating types of questions. And they often mix multiple concepts, so Newton's laws and different graphs and speeds and stuff, and it all can get a bit confusing. And particularly that higher tier content such as momentum and pressure and fluids can feel unfamiliar. And if you're not confident in maths, for example, it can get really quite tough and intimidating. So here are some things which you can do to try and help you feel more confident. So firstly, it's knowing your equations. And yes, you do get given your equations at the moment, but it's not just a case of being able to memorize and see those equations. You just need to understand what each variable in each equation means. And also be drawing diagrams. If a question doesn't give you one, it can be useful to sketch the force or collision or reaction or movement happening, even if it doesn't come part of your answer, and maybe do it somewhere else, but it can be helpful on a separate piece of paper to try and visualize what you're answering a question about, even if it's just calculation basis. It can help determine what are the moving parts and what is the bit that you need to be identifying. So that can be a really useful little trick. Also, watch those command words as well. So remember that state is given just a 1 mark fact, whereas explain, you will need to give both a link to a cause and an effect. And if it's evaluative, you need to be discussing both sides of an argument. So firstly, identifying what those two sides are, and then making sure you refer to both. And looking at the number of marks to give a guide to answer length is really useful in this type of question, because it can help you kind of understand what you need to be doing in order to get the marks, which can help break it down in the mind and just give you some time to calm down before putting anything from pen to paper. Just break it down on those long questions, underline the key values and goals within the question, and it can help just get to that point of being able to solve something step by step, because even those partial workings can get you extra marks. And then use your graph skills as well that you've learned, not just in physics, but in chemistry, physics, biology and maths. Understand what the gradient and area are showing on a distance, time and velocity time graphs, for example, and if you do need to, using rulers and labelling everything clearly can just help you set everything in your mind a bit better. And then finally, just practicing those wordy problems. So often you'll get real life context such as drivers, parachutes, cranes and collisions. So just linking everything back to those forces, that bits of motion, or the idea of energy transfers, linking it all back and breaking it down, stripping down the context in order to understand what the question is, and then putting that context back in once you understand the scientific concepts relevant to the question in order to produce a well-meaning answer. So let's go through the unit in turn to see what you need to be knowing for your exam. So to start with, scalars and vectors. So you need to understand that scalars have magnitudes only, whereas vectors have magnitude and direction, and that vectors can be represented by arrows, where the length is referring to the magnitude and the arrow is the direction. And for each of these topics, I'm going to list the command words above, and what you'll be able to do is download this slideshow as a PDF. And as you go through each of these in your final stages of revision, I want you to go through each of the topics, look at the command words, and think, how can I talk about this topic using those command words? So how can I identify scalars and vectors? How can I define scalars and vectors? And how can I distinguish between them? And that'll be just a practice that you can use to kind of get yourself prepared for something that you might be likely to be asked in the exam going into it. So you may be asked to distinguish between scalars and vector quantities, or draw and interpret vector diagrams. So this is what I'm going to give you for each subunit within each of our P5 to P8, and hopefully you can then go away and feel confident in going through the rest of the content in more detail and being able to feel confident going into answering all different types of questions. So let's move on to the next topic, contact and non-contact forces. So forces can be contact, which could be friction, tension, air resistance, or non-contact, which could be more referred to gravity, magnetism, and electrostatic forces as well. And that force is really just an interaction between two objects, which can be physical or at a distance. So it can be contact or non-contact. And just remember that all forces are vector quantities. So you want to be able to expect to describe the interaction between objects and classify the forces involved as well. So for gravity and weight is calculated through mass times the gravitational field strength, and understand that weight is a force or a vector measured in newtons and acts through the object's centre of mass. You also need to know that weight and mass are directly proportional and can be measured using the Newton meter. So you might be asked to calculate the weight, explain the differences between mass and weight, or use that proportionality symbol as well. For resultant forces, you need to understand that a resultant force replaces multiple forces with a single force with the same effect, and that can be calculated when forces act in a straight line. So for higher tier only students, you also need to be able to talk about how resolve forces into components at right angles, and use free body diagrams as well, and vector diagrams to demonstrate forces in equilibrium. So expect to calculate resultant forces, draw diagrams, and if you're higher tier, using vector diagrams in equilibrium questions as well. For moments, levers and gears, which is a physics only unit, you need to be able to define a moment and calculate a moment using our equation, m equals F times d, and also understand that a balanced object means that the total clockwise moment equals the total anti-clockwise moment, and that levers and gears transmit rotational effects and can increase force or distance. So you might be asked to calculate moments, recall the equation, or explain how gears and levers work. So make sure that when you're going through this moments, levers and gears unit, you can cover each of these points and answer a question about it. For pressures and fluids, which again is a physics only unit, you need to be able to recognise that fluids exert pressure at right angles to any surface, and that surface pressure can be calculated with pressure P equals force times area. If you're a high school student, you also need to be able to use the equation that pressure in a column can be calculated as height times density times gravitational field strength, and that pressure increases with density and depth, and you need to be able to explain that as well. And finally, that uneven fluid pressure causes upthrust, which is what makes a product, or an object rather, float or sink. So you might be asked to calculate pressure or explain why pressure increases with depth in a liquid. So now let's move on to atmospheric pressure. So atmospheric pressure is caused by air molecules colliding with surfaces, and it has the height above Earth increases, atmospheric pressure decreases because there are fewer air molecules above at higher altitudes, so the weight of air is less. So expect to explain why atmospheric pressure decreases with altitude using the particle model. So now let's move on to distance, speed and velocity. So distance is how far an object moves, which is a scalar quantity, and displacement is the distance in a straight line from the start to the finish, so that's a vector because it's a distance and a direction. Speed can be calculated using distance over time, and velocity is the speed in a given direction, which makes it a vector quantity. So you might be asked again to compare the scalar and vector quantities in relation to distance, speed and velocity, or calculate that speed using that distance over time equation. For acceleration, you need to be able to calculate acceleration as the change in velocity over time. And if you're higher tier only, you also need to be able to use a more complicated equation as well. You also need to know that acceleration is measured in meter per second squared, and that deceleration is essentially negative acceleration. So for this one, you may be able to recognise velocity time graphs, so expect to calculate acceleration from those, or simply interpret what happens during a vehicle's journey through acceleration and deceleration on a graph. And if you're higher tier only, and if you're higher tier, you need to be able to use the area or the gradient of velocity time graph for some motion analysis or calculating that acceleration rate as well. So let's move on to Newton's laws. So for Newton's first law, you need to understand that if a resultant force on an object is zero, a stationary object will stay still and a moving object will keep moving at a constant velocity. And if you're higher tier, you need to be able to understand the concept of inertia, where objects resist changes in motion. So expect to explain whether an object will accelerate or remain in a steady motion based on whether forces are balanced or not. For Newton's second law, you need to be able to understand that a non-zero resultant force causes acceleration, and the acceleration is proportional to the force and inversely proportional to mass, which gives us our equation force equals mass times acceleration, and force is measured in newtons. So you might be asked to calculate the force, mass or acceleration using that equation, so you might be expected to rearrange that equation to calculate mass or acceleration as well, and simply describe how they're all related. For Newton's third law, you need to understand that for every action there is an equal and opposite reaction, and the two forces act on different objects, and this applies on all interactions equal in equilibrium. So expect to identify the interaction pairs firstly and use that principle to explain how they are equal and opposite. So you also need to be able to talk about our required practical of acceleration. So we might, as we've said before, describe how you can investigate how changing the force or mass changes acceleration related to Newton's second law, and describe that common setup using either trolleys or pulleys and light gates as we described when we went through the required practicals. And then finally using graphs or calculations to find the acceleration, and potentially using your results to support Newton's second law as well. You also, for physics students, need to be able to talk about stopping distance. So stopping distance is that thinking distance plus the braking distance, and that can be affected by the speed that the car was going at or the vehicle was going at, the driver's reaction time, what could be affecting that, road conditions, weather conditions, and simply the car condition as well. So the quality of the brakes, the quality of the tyres as well. And you'll often be given graphs to show how stopping distance increases with speed. So you need to be able to estimate those stopping distances or interpret a stopping distance graph from real life scenarios and think about what could be affecting that. So if it's a driver's reaction time, it could be tiredness, use of alcohol or drugs or similar, and any other conditions as well. And finally, going through our last few units here, you also need to be able to talk about the braking and energy transfer if you're a physics student. So talking about how the braking force does work on a vehicle, and that transfers kinetic energy into heat energy, which increases with the brake temperature. So if you're at a greater speed, more braking force is needed to stop in a given time, and also need to understand that those large decelerations can cause overheating or skidding, which is related to the work being done on the vehicle or the elements of the vehicle. So expect to link that braking distance with kinetic energy, and or just simply describe how stopping involves that energy transfer. Now finally, if you're a higher tier student, you need to be able to talk about momentum. So momentum is the mass times the change in velocity, And in a closed system, momentum is conserved during collision. So you need to be able to calculate momentum before or after an event and apply that principle of the conservation of momentum. And also you need to be able to talk about changes in momentum as well. And that could be the force, and the force is calculated by the change in momentum divided by the change in time. So that is that rate of the change of momentum. And increasing the time reduces the force in a collision, which is why safety features such as seatbelts, airbags and crumple zones are really beneficial to increasing the time between that change in momentum, which can make something a lot more safer as well. So expect to justify how these safety features reduce injuries using that idea about momentum and time and how they are linked together. So that's all of the parts of P5 all come together in one long explanation of what you need to learn. So I think now would be a good time for you to either have a go at the P5 revision clocks, or if you do feel quite confident on this topic already, move on to our range of P5 questions underneath this video. And then once you're ready, we'll come back and go through P6. Okay, so let's move on to P6, which is waves, and we're going to do the same things we did for P5 by running through all of the key concepts that you need to go through during your revision. So let's start with transverse and longitudinal waves. So you need to understand and describe that transverse waves are oscillations which are perpendicular to the direction of the energy transfer, which examples of that include water waves and electromagnetic waves, whereas longitudinal waves are oscillations in parallel to that energy transfer, such as sound waves. And sound waves in air show compressions and refractions, and for both types it's the waves that moves, not the particles, which is incredibly important to understand. So you might be able to describe the differences between wave types, or just explain that waves transfer energy, not the matter itself. And we also need to know the properties of waves, so that includes the amplitude, which is the maximum displacement from rest positions, the wavelength, which is the distance between matching points on adjacent waves, frequency is the waves per second, which is measured in hertz, the period of a wave, which is 1 divided by the frequency, the wave speed, and if you're a physics only student as well, you need to be able to describe how it changes in different media and how velocity, frequency and wavelength are linked. So you might be asked to calculate that wave speed, identify the amplitude or the wavelength on diagrams, or use the period equation as well. So for your required practical, which is wave speed, we have done a practical to investigate the speed of waves on a ripple tank, in a solid, and sound and air as well. So you might be expected to measure the wavelength, frequency and calculate speed using our wavelength equation as well. So you might be able to describe the method, identify the suitable equipment, or evaluate the accuracy in your measurements in a similar way as we described when we went through the required practicals earlier. And if you're a physics only student, you also need to be able to talk about reflection, transmission and absorption. So the idea that waves can be reflected, transmitted or absorbed at boundaries, and specular refraction as well is on a smooth surface, and diffuse reflection is on a rough surface. And ray diagrams can be shown to show the paths of wavelength, light waves and reflection, and also calculate different angles as well. So expect to draw ray diagrams or just explain what happens when a wave meets a new material. For the required practical of light, which is, as we already said, a physics only practical, you need to be able to investigate the reflection of light by different surfaces, or investigate refraction of light through different substances. So you might be needing to measure the angle of incidence and reflection or refraction using ray boxes and protractors. So you might be explaining that refraction, evaluating results, or identifying the variables and controls in our required practical as well. And a great place to start with required practical revision, if you haven't already, are our required practical cheat sheets, which can be found on our website. And another physics only and higher tier only topic are sound waves. So sound waves travel via vibrations through solids and air. Vibrations in solids create movements of particles, such as an eardrum, and that is related to our hearing range of 20 to 20,000 hertz or 20 kilohertz. And you also need to be able to convert between sound waves and vibrations over a limited frequency range. So expect to see questions on how sound waves cause hearing and why some frequencies can't be heard as well. Another physics only and higher tier only topic, I apologise, there's quite a few of these in these topics here, is waves for detection and exploration, so the practical uses of waves. So ultrasound is an example, so those are frequencies above that 20 kilohertz of the human hearing range, and they can be used for medical imaging, echo sounding and industrial scans as well. So you also need to know that they reflect at boundaries and that there's a time delay to calculate different distances, which is really useful in underwater exploration. You've also got seismic waves, and there are two different types. You've got P waves, which travel through solids and liquids, and S waves, transverse, which only travel through solids. And seismic waves helps us understand the Earth's internal structure, for just one example. So now let's move on to the second part of our unit, which is about the electromagnetic spectrum. So electromagnetic waves are transverse and transfer energy from a source to an absorber. And all electromagnetic waves travel at the same speed in a vacuum. The electromagnetic spectrum is arranged by wavelength and frequency. So you start with radio waves, then microwaves, then infrared radiation, visible light, ultraviolet, X-rays and gamma rays. And yes, I was thinking of the song as I was going through that just then. And visible light is the only part which is detected by the human eye. So expect to name that spectrum in the correct order and describe how the wavelength frequency will change across it as well. And if you're a higher tier only student, you also need to relate these to refraction and wave behaviour. So the idea that different materials can absorb, transmit, reflect or refract electromagnetic waves. Refraction occurs to a change in wave speed when entering a new medium, and that ray diagrams and wavefront diagrams can show how that refraction works. So you might be able to draw or interpret those diagrams and also explain how speed affects the direction of waves. So in relation to a required practical for the infrared radiation, which is the radiation and absorption practical we went through, so we want to be talking about how to investigate how different surfaces absorb or emit infrared radiation, compare surfaces like shiny metal, matte black or white paper, which can be done with a Leslie cube, as we can see on this slide here, and use these informations to identify which is the best absorber or emitter. So you might be asked to describe that practical, interpret some results, and also suggest reasons for differences between the surfaces. Alongside all of the points of what we discussed, they might ask about this practical in the exam in our previous slide. If you're a high tier only student, you also need to be able to describe wave interactions with atoms. So the idea that radio waves can be produced by oscillations in electrical circuits, and when they're absorbed, they can create an alternating current in a receiver. Gamma rays, another example, can come from changes in a nuclei, and that electromagnetic waves can be emitted or absorbed during changes in atoms or nuclei. So those are the key concepts in those wave interaction with atoms. So be able to expect to link electromagnetic wave production to electron or nuclear changes and to circuits as well if you're a higher tier student. We also need to be able to talk about the dangers of electromagnetic radiation if you're a higher tier student. So that includes the idea that UV, X-rays and gamma rays can be hazardous. So UV light can premature skin aging and cause skin cancer, which is why it's important to use sun cream, for example. And X-rays and gamma rays are ionizing, which means they can cause gene mutations or cancer. The risk of these depends on the types of radiation you're exposed to as well as the dose. And you also need to know, in relation to P4 actually, that radiation dose is measured in sieverts as well. So you may be asked rather to evaluate the risks using data or compare different just types of EM radiation and the dangers from each of them. As a high tier student, you also need to know the following potential uses of electromagnetic waves. So if you're a high tier student, you want to know why each wave is suitable for specific uses. So for example, radio waves for TV and radio signals, infrared for heaters and night vision, remote controls, X-rays for medical imaging, UV light for sunbeds, security pens, sterilisation, and basically just expect to match these uses on this table here, or just explain why a wave is suitable for a specific purpose. So it can be really helpful for this kind of question to have these sorts of tables with the different waves and their potential uses as well. And we also want to be talking about lens and ray diagrams in waves as well. So we need to know the uses of convex lanes, which focuses light to a point, and concave lengths, which spread out light. And ray diagrams can be used to show these light paths and image positions. And we also need to be able to use the magnification equation, which is image height divided by object's height, in order to kind of basically explain how lenses and ray diagrams are used. So expect to draw ray diagrams and calculate magnification to discuss and present that you understand how lenses are used for practical purposes. If you're a physics tier student, you also need to know about visible light and that relation to colour. So each colour, essentially within our visible light part of the electromagnetic wave spectrum, has a specific wavelength or frequency, as you can see from the diagram to our right. And that white objects reflect all wavelengths, whereas black objects absorb all. And then everything in between is a mixture, essentially. You also need to understand that filters can absorb some wavelength and transmit others, which is what causes the colour. And if it's transparent, it means that it transmits all the light, and if it's translucent, it scatters some of the light. So you might need to be able to explain how an object's colour is seen and how filters affect light. And then the final concept for P6 for physics only students is black body radiation. So you need to be able to describe and explain and interpret different contexts to explain that all objects emit and absorb infrared radiation, and a perfect black body is described as being the best absorber or emitter of light. Hotter objects emit more radiation at shorter wavelengths, but at a constant temperature, the rate of emission equals the rate of absorption. And finally, and the final key point, is that the Earth's temperature is affected by absorption, emission, and the reflection of radiation. So expect to explain temperature changes in terms of that radiation balance, or interpret diagrams or data of radiation and relate it to black body radiation. So that's everything for P6. So now would be the perfect time to either do the revision clocks, or if you're ready, do the range of questions underneath from the revision hub. And then once you're ready, we'll move on to P7. So welcome back, everybody. We're going to go through magnetism and electromagnetism now. If you're a combined student, this is your final topic, and if you're a physics student, this is your penultimate topic. So let's start with the idea of magnetic poles and magnetic materials. So you need to be able to describe that the poles are where the magnetic force is strongest, and like poles repel, unlike poles attract, and these are non-contact forces, which is related to P5. Permanent magnets produce their own field, whereas induced magnets become magnetic when in a field and lose magnetism when removed. So that's the difference between permanent and induced magnets. And also that induced magnets always attract. So you may be asked to describe interactions between magnets or explain the differences between permanent and induced magnets. Our second part of the topic is magnetic fields and compasses. So a magnetic field is the region where a force acts on a magnet or a magnetic material such as iron, steel, cobalt or nickel. And field lines point from north to south, and field is strongest at the poles and weaker further away. So you may need to understand how a compass can be used to plot field lines, and finally understand that the Earth has its own magnetic field, and that's why compasses align with it. So expect to be able to draw a bar magnet field or explain how that compass evidence suggests that the Earth's core is magnetic. We also need to be able to talk about electromagnetism and solenoids. So a current carrying wave produces a circular magnetic field around it, and a field strength increases with current and decreases with distance. A solenoid or coiled wire produces a strong uniform field similar to a bar magnet, and adding an iron core is what makes it an electromagnet. So you may be asked to draw field patterns or explain how a solenoid creates a stronger magnetic effect. If you're a higher tier student, you also need to be able to talk about the motor effect. When a wire is carrying a current, is in a magnetic field, it experiences a force. The force is at a right angle to both the current and the magnetic field. Fleming's left-hand rule shows force, which is the thumb, the magnetic field, which is the first finger, and the current, which is the second finger. And the equation for this is force equals magnetic flux density times current times length. So you need to be able to apply the rule or equation to questions involving the direction or size of a force to show the motor effect. And again, if you're a higher tier only student, you need to be able to understand electric motors. You need to be able to explain and describe them. So for example, principles such as a current in a coil within a magnetic field produces a rotating force, and the motor continues to speed in this rotating force due to a split ring communicator. And this is used in devices such as fans, drills, or hair dryers. So you may be asked to explain how a current carrying coil produces rotation in a magnetic field. And I appreciate we're only going through these quickly now, but if you do want to have a bit more in-depth on these topics, you can look at our videos, which will be available for free on the week leading up to the exams. So have a look at those videos now. I'll link them below, and hopefully that will give you a strong foundation on these kind of topics. If you're a higher tier student, you also need to be able to describe loudspeakers and how they are used. So we want to be using the principles of the motor effect to explain that they convert electrical signals into sound waves, and the coil moves back and forth in a magnetic field when that current varies. And that is what creates the pressure variations in the air, which result in the sound waves. So you need to be able to explain how the motor effect produces movement and how that relates to the sound, which is similar to what we were talking about in P6 waves. Again, another higher tier student only topic, you need to be able to talk about induced potential and the generator effect. So this is ideas such as recalling and applying the ideas that moving a wire in a magnetic field induces a potential difference, and if this is in a complete circuit, it induces a current called the generator effect. An induced current creates a magnetic field that opposes the change, and this can be affected by the speed of movement, the strength of field, or the length of wire. So you may be asked to explain how induced current is created or how those factors we just discussed affect it. You also, as a higher tier student, need to be able to discuss the uses of the generator effect. So this could be explaining the use in alternators to generate an alternating current by rotating a coil in a magnetic field, or the use in dynamos to create a direct current using a split ring commutator. And the output can be shown as voltage versus time graphs. So expect to compare AC and DC generators and interpret graphs of induced potential as well. And another final high tier only topic is the use of microphones. So you want to be able to use the generator effect to describe how that converts sound pressure variations into electrical signals in a similar way to loudspeakers, and vibrating the diaphragm moves a coil in a magnetic field which induces that current. So you might need to be explaining how that induced current is created, and again how factors change it. The final topic is the national grid and power transfer. So you want to be able to justify, evaluate and explain the use of magnetism and electromagnetism in the national grid and power transfer. So electricity is transferred efficiently by using high voltage and low voltage current, by using high voltage and low currents, which is what we discussed in national grid in paper 1. and this uses the principles of step-up and step-down transformers. So step-up transformers increase the voltage for transmission, and step-down transformers reduce the voltage for homes, and this reduces the energy loss due to the heating and wires. So this is something we heavily discussed in P1, but it's relevant here as well. But at this point, you're explaining it at a slightly higher level, so you might be asked to explain why high voltage is used or evaluate the efficiencies of the system, and talk about the use of coils and the calculation here as well, which is part of the specification, in order to relate all of this to the generator effect and induced potentials. So now it's your turn to talk about P7 on the revision clocks, putting all of your knowledge into one place and then using that to identify gaps in your knowledge that you need to go back to, or you can simply have a go at the P7 questions now Revision Hub underneath. If you're a combined student, you don't need to continue with this video, and I'll leave you here and say good luck with your exam. Whereas if you're a physics student, please go and do those and then come back to this video so we can go through P8 together. So welcome back to our final unit of physics GCSE, which is space physics. So this is a slightly shorter topic, which we can go through quite quickly here, and then I'll leave you to it to go through your own personal revision. So firstly, our solar system. The solar system consists of the sun, 8 planets, dwarf planets, and natural satellites such as the moons. The sun formed from a nebula, which is a cloud of gas and dust pulled together by gravity. Fusion began in the core and released energy released balanced gravitational collapse. And also you need to understand and describe that our solar system is just a tiny part of the Milky Way galaxy. So the main things here are being able to explain how gravity caused the sun to form and how the fusion led to a stable star to create the foundations of our solar system. And then the second part of this unit is describing the life cycle of a star. So you need to be able to describe and explain this, all the life cycle stages such as the nebula, the protostar, the main sequence star, the red giant, the white dwarf, and the black dwarf. And for stars much more massive than our sun, they also become a red supergiant, undergo a supernova, and then become a neutron star or a black hole. You also need to talk about how fusion, which is related to the star, forms all naturally occurring elements, and those heavier elements, all of those above ions, are only formed during supernovae. And supernovae scatter elements across the universe, which helps explain how essentially the universe was created. So you may be asked to describe each stage or explain how fusion produces new elements. So you also need to be able to talk about orbital motion and satellites. So the idea that gravity keeps planets, moons and satellites in a circular orbit, and that artificial satellites orbit Earth for communication, weather and navigation, which are the ones that we basically put up there. For higher tier students, you also need to be able to discuss circular motion. So the object speed is constant, but the velocity changes because the direction changes, and also discuss that if the orbital speed changes, radius must change in order to remain stable. So expect to compare natural versus artificial satellites, or explain the link between orbital radius, speed and stability. And finally, the final part of this unit and the whole of GCSE physics is redshift and the expanding universe. So you want to be able to discuss and explain and interpret how light from distant galaxies appear redshifted, which means their wavelengths are longer than they actually are. And the greater the redshift means that the faster the recession, which means that these galaxies are further away from us. And this gives us support that the universe is expanding and supports the idea of the Big Bang Theory, which is that the universe began from a hot, dense, small region and has been expanding ever since. And since 1998, the evidence from supernovae suggests that this expansion is accelerating, which is very exciting that we're able to kind of understand these kind of things and produce these theories. So you may be asked to explain that redshift, link it to galaxy motion, or describe how it supports the Big Bang Theory. And finally, actually, one thing we haven't discussed yet, which we should have done in space physics, is those unanswered questions. So we kind of just need to link all of this together to talk about how scientists use observations to build theories, but some phenomena remain unexplained. So we understand a lot already, but there's actually probably more we don't understand than that we do understand. And examples of these is dark matter, which adds to gravity but doesn't emit radiation, and dark energy, which may explain the accelerated expansion. But really, we know these things must exist, or something must exist from calculations, but we have no idea how these actually work or what they actually are. And that's where a lot of research in this field is going on at the moment. So those are some extra things that you might be asked about in exam questions. So that might be linked to your more AO3 scientific principles, where you might need to discuss the unanswered evidence or the unexplained evidence, and basically suggest how scientists are uncertain about this and explain why this is important for all of science in general. So expect to acknowledge that science is evolving and not all of the aspects of the universe are fully understood. So now it's time to complete the revision clocks for P8 or have a go at our range of P8 questions linked underneath on the revision hub. But that's it from me. Good luck with your physics exam. And I know for many of you, this will be one of your final exams. So congratulations about getting this far with your GCSEs. And you should be really proud of what you've achieved over the last few weeks. please keep practicing your physics questions, keep going through those key principles and keep that momentum going into your final exam. So good luck, all the best, and after they're done, enjoy your summer.